Recording. Before I jump into the graph thing, I'd like to show you one definition which I skipped in the last class, the inertial definition of mass. So inertial mass, or usually the mass of an object, is defined like this. A mass of a body is determined by the second law of motion from the acceleration of the body when it is subject to a force that is not due to gravity. That's something. And mass is also defined as the measure of the property of inertia. In one way we can define the term mass can be that what is the amount of material within that object. So mass is measured in kilogram, which is the SI unit for mass. The initial concept for mass is something like this, that mass is one of the significant property of an object which is responsible to prohibit, or in other way you can say it prohibit, I should say prohibit, it opposes is a better word. Prohibit might as well be completely. So mass is one of the property of an object which opposes the change of its velocity. To be honest, there is one composite quantity that would be taught a bit further down in the syllabus, which is called momentum. Momentum is actually the quantity that is obtained by the multiplication of mass times velocity. Although momentum can be defined by a whole lot of different set of equations for higher degree of physics, but the very basic definition for momentum is mass times velocity. So together these two quantities actually determine that how difficult it is for us to change the velocity, existing velocity of an object. If you have a higher momentum of an object, you would require more effort to change its velocity, which can be easily understood for a simple example. Let's say for a single human being, it is pretty difficult to stop a long bus or truck, maybe going at only 10 kilometers per hour. It's difficult for a single person to stop. Although the speed is not quite high, but because the mass is quite massive, it tends to be difficult to stop. And similarly, if you think for a bullet shot of a gun, the slug of the bullet, which is basically the projectile that shoots out of the bullet, that has a very small mass, maybe within the range of a couple of grams. But because it moves with such a high speed, it is also very difficult for a single person to stop. We're talking about regular people, not Superman, Batman, or other people like Green Lantern or Neo in Matrix. Regular human being, difficult to stop a bullet. So both of these properties, mass and velocity, together actually gives us a measure that how difficult it is for us to change the velocity of an object. Momentum happens to be that quantity, which gives us a measurable quantity of that opposition amount. That's the physical significance for momentum. Tyson, I think you raised your hand. Do you have a question?
Sir, should we note it down?
Sorry?
Should we note it down like this one?
বুঝি নাই.
Sorry, এটা কি note করবো?
No. You don't have to write anything. For the time, you don't have to write anything unless I ask you to, but keep your copies in your hand. Within the graph class, there is some small stuff that I'm going to ask you to write, but for most part, you don't have to write anything. All right. So I'm going to jump directly into the graph discussion. Many of you actually know how to handle graphs. You might have come across a lot of graphs in your math classes and so on and so forth. But still, I have a way to teach the graph things, and I'm going to pick that up. Any graph, whenever we have any graph, let's say this is a graph of a variable y-axis divided by x-axis. Typically, always we define the x-axis as the horizontal axis, y-axis as the vertical axis. Usually, I'm not saying it's always, but typically, we try to plot a graph where on the x-axis we usually set the independent variable, and on the y-axis we set the dependent variable. Now, let me elaborate these two ideas a bit. Independent variable is something that either you can choose the value of this variable as at your wish, or this variable is a continuously changing variable which you can choose, but you cannot pace it. For example, time is one of the most common independent variable. If you're performing an experiment, if you're trying to measure something for a certain duration of time, you can start your observation at certain time instance, which for your experiment, you're going to define as initial time, which is t equals to 0 second, or minute, if you're preferring the minute unit. Second happens to be the SI unit for time. That's why I'm using the second sign. And then you can perform your observation for a duration of time period, for a duration of time. And then whatever the change of the variable, other variable that you're seeing, you can plot it with respect to time. So as time is going to go further, you can plot the value of that thing with the different relevance of the time. And dependent variables are those which are dependent on the time variable. For example, if I prefer to give you a simple example, for example, if we have a hot object, let's say an object, let's say the room temperature is 25 degrees Celsius, temperature of the room, and then you have a hot object that you took out of an oven or a heat source, let's say that's temperature is 80 degrees Celsius. If you keep it in contact with the atmosphere and try to measure the temperature of the object over time, you're going to see that from 80 degrees Celsius, let's say in this case, the y can be the theta degrees Celsius, and time can be given in, let's say, minutes, because typically for thermal experiment, we prefer to give minute because thermal experiment typically takes a significant amount of time in between observations, not like, unlike motion scenarios. We could also use second, doesn't matter. Whatever the variable that you choose, that's simply gonna take care of how often your observations are gonna be. So if we make a observation for this experiment that an 80-degree hot object is starting to cool down while in contact with the atmosphere, and then you can start taking those readings using a thermometer. Let's say at 0 second you have 80 degrees Celsius. After 1 minute you have some other temperature, and then other temperature. So as time goes by, your temperature slowly loses. And if your observation is correct, you're going to end up with a graph that is going to be slowly losing gradient. Now, why does it lose gradient? That's a different issue. I'm not talking about that, but that's basically how the graph works. Now, I said at the beginning that usually we place the independent variable on the x-axis and the dependent variable on the y-axis, but there can be changes of this rule as well. For example, in some cases, you can also put two dependent variables which are dependent on each other, not with respect to a very exclusive independent variable on the graph as well. Graphs can be plotted with any variable versus any variable, which two have a correlation between each other. So you can, but the variables preferably has to be related somehow. I mean, one of them has to be affected by the other or vice versa. And the important thing is that whenever we describe a certain graph, we always try to describe a graph something like this. Let's say this is y, this is x. So we're gonna say y versus x. So if you're drawing a temperature versus time graph, we might as well say this is a theta dash t graph, or we can say this is a theta versus t graph. That can also work. The y-axis variable is always mentioned at the beginning. The first we mention the y-axis variable, next we mention the x-axis variable. This is always the way we describe a graph. So if you're plotting a displacement time graph, we might say that we have displacement versus time graph. If we are plotting a velocity time versus time graph, we might say a velocity versus time graph. If we're plotting a speed time graph, we might say speed versus time graph. So I'm using the vector symbols over here just to make a differentiation between velocity and speed. But usually for your syllabus level, we do not typically use the vector sign on the graph axis, because the change of value of a vector quantity can actually shown by where that points are plotted. For example, you can have positive values on the positive y-axis, you can have negative values on the negative y-axis. So these two opposite type of values, positive and negative, might actually refer to us about the direction of the object. I'm going to talk about this more detail in the velocity time graph section, so which is going to show up just after a while. But this is the basic idea. It's the first thing that you have to understand, that whenever we are describing graphs, the first variable that we mentioned for the graph is always the y-axis variable. The second variable that we mentioned for the graph is always the x-axis variable. The next thing that is important for us to understand from the graph is that any graph primarily tells us a couple of things. Let's say, okay, y by x. If you have a graph of y versus x, let's say that graph looks somewhat like this. The first set of information that we get out of a graph is for any given value of x, we can find out the relevant value of y. For any relevant value of y, we can find out the relevant value of x, which is basically using the scale. So if I ask you that from the graph, what is the value of y for x equals to this much? So you can read out from the graph that, well, we are asked to find the y value. So we just trace that line onto the graph over here and trace it back onto the y-axis. And that's basically your relevant y-axis value. Likewise, if you are given a y-axis value, maybe somewhere over here, and you are asked to find out the possible x-axis value, you can also do the opposite way, and you can find the relevant x-axis value. It is possible for certain graphs to have multiple different values for one single value. For example, whenever you have a periodic graph, let's say a sine curve like that. Let's say this is the VT graph for a certain object. And if I ask you that, what are the time instances for which the velocity of the object was this much? So when the velocity of the object was this much. So to get this thing, you might as well consider all the time instances where the graph is having this velocity value. So this is one of your time answer. This is another time answer. If you further increase this point, you're gonna get another value over here. You're gonna get another value right over here. So all of these individual time instances are the individual time answers when the value of the velocity of the object was this much. So you can have multiple different answers depending upon the shape of your graph. If it's a circular graph, you can also have repeated values. This is not essentially a circular graph, but it's in terms of graph, it's a very close resemblance of a circular graph because you have repeated answers. That's basically how you can have multiple different values. That's information number one that we get out of a graph. The second information that we get is how y changes with respect to. There's a short form that I write a lot with respect to, but you can understand it in the bigger form with respect to how y changes with respect to x. So this is basically what we mean by the term gradient, or sometimes we can also use the term slope. They both are the same term, so I might be using them alternately in my discussion, but you should understand them by the same amount. Gradient or slope of a certain graph is given by the expression m equals to delta y by delta x. Now, delta y by delta x basically means that how much change of the y-axis variable happens over a relevant amount of change for the x-axis variable. Dealing with the gradient of a graph is actually pretty simple, provided you know how to handle that. Now, for straight graphs, it's actually really simple. If you have a straight line graph, let's say y versus x, then you have a graph that maybe looks like this. If you are trying to find out the gradient of this thing, straight lines have a constant gradient because that's how straight lines are defined. I mean, lines which have a constant gradient are defined as straight lines. They are not going to curve. So they basically have the same gradient everywhere. Now, if I tell you that, what does it mean that they have the same gradient everywhere? It simply means that no matter how big of a delta y or how big of a delta x or small fraction of the graph that you choose, and no matter where you measure it, you are going to end up with the exactly same value for the same ratio calculation, because all of these triangles are going to be similar triangles. Which triangles I'm talking about? So for example, let's say if you want to measure the gradient of this straight line for a triangle that is, let's say, this much big. So in this case, this is going to be our delta y segment. This is going to be our delta x segment. You can find out the ratio of these two things, and that's going to be your gradient value. So m equals del y by del x, which is very much possible. On the other hand, you can choose this triangle to be significantly smaller. For example, if you want to measure it for a triangle of this much size, let's say if you want to measure it for a triangle of this much size, this is our blue delta y by blue delta x. So in that case also, the gradient should be delta y by delta x. If your calculation is right and if your drawing is all right, then you should always have the same ratio values, because you should be seeing from here that having this angle common and this 90 degrees common in between both the triangles, they are basically similar triangles. So the ratio of similar sides gives you the same ratio. You cannot have dissimilar ratios for the ratio of similar sides. That's not going to work out. So no matter where you measure it, no matter how big of a section or how small of a section that you choose to measure the gradient of a straight line, provided your calculations are right, all right, you should end up with the exact same value no matter where you measure it. What we recommend for the sake of more reliable answer is that whenever you have a certain line and you're trying to measure the gradient of that line, you should preferably choose good cross points and secondly, you should preferably draw a large triangle, and then if this graph is responsible from some practical experiment, you should preferably avoid any plotted point. Even they are on the graph. Now, what do I mean by this? Let's have a look. A good cross point would mean that you have the, let's say you have the grid system of your graph. I might as well bring up a grid from here. Okay, tutoring material, there you are. Any year question is good. Pick up a graph. 31. I could have used the grid of the whiteboard as well, but I just have a preference not to use that for a certain reason. I'm going to explain that in a bit. So just bear with me for a while. Can we get the full graph here? Please accommodate. All right, beautiful. We can. No, not this one. Okay, let's say we have a graph like this, and we're about to draw a straight line through this graph. So let's say this is our y-axis side, this is our x-axis side. And I'm going to zoom in on this graph because I want you to be able to see what do I mean by a good cross point. Let's say one of the straight line that we are about to draw, I'm going to choose a sharp line. So let's say I'm going to choose this one, small dot. Let's say this is one of your line for which you are trying to draw the gradient. You should preferably choose a good cross point. A good cross point means that what you need to understand that on your from your axis plotting on the given graph on the y-axis and the x-axis, you should be able to know, you should know the increment size of a single y-axis box. Let's say this much, or maybe this much, or maybe this much. So you should be able to measure that, and you should be also able to measure the smallest increment on the x-axis as well. So each of these small increments should be also known to you. It's usually easily measurable. So your job is to choose such a point for the corner of the triangle so that your measurement for the delta y and delta x, for that purpose, you don't have to rely upon your imagination or your guess. For example, if I choose maybe this point, let's say this specific point for the corner of my triangle, and maybe if I choose on the left side close to here, if I go ahead and choose maybe this very point on the very left, these two can be said to be pretty good of a choice because this line is going through the cross point of the grid lines. However, if you, for whatever reason, choose, let's say one of these points, let's say if you want to choose this green point right over here, now you have a difficulty to actually measure how much should you read off for this much part. How much should you read off for this much part, because you have this much arbitrary section over here. It might appear to be half, but are you sure it is exactly 0.5? You don't know that. And similarly applicable for any of the points you will choose somewhere over here. Let's in that case, you have to guess how much is this. So it is recommended that you preferably do not choose points which does not pass through a perfect crossing point of the given grid. For this straight line that I arbitrarily drew, it looks pretty much straight, but might not as well be straight because I hand drew this line. So my preferable choices for these graph points might as well be this, and then this can be also used for that purpose. I can also use this maybe. This I don't like very much because it's a bit far away. And if I go further down, I could choose this one. This is a very nice point. This one is also a very nice point. Going down further, we have a bit of a deviation, 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 more deviation, more deviation. Then this is a good, nice point. This is a good, nice point, and nice point, and so on and so forth. Do you guys understand what I'm trying to mean over here? That choosing a good crossing point. Does this concept make sense?
Yes, sir.
বুঝা গেছে? So এটা হচ্ছে একটা primary জিনিস that we should preferably choose a good cross point of the graph for our purpose. The second point is that we should preferably choose a large triangle. Large triangle means, if you wonder that why should we choose a large triangle? There is a reason for this. The physical reason is something like this. Geometrically, how do you define a point? I mean, what is the geometric definition of a point? A point in geometry is defined to be basically a location, or it's basically a coordinate. If you want to define it in solid geometry terms, a point is something that only has existence. It does not have any dimension. It doesn't have length. It does not have width. It doesn't have height. It is basically impossible for us human minds to even imagine a point, because whenever you're trying to imagine anything in your head, you are going to see it with some dimension. Without dimension, you cannot imagine anything. None of us can, as far as I know. So a point basically means something which has only the existence, or in other words, I can say it is basically the location or the coordinate of a certain location. That's basically what we mean by a point. Whenever we extend a point, whenever we are trying to move a point in only one axis, that basically becomes a line. A line is supposed to have one dimension of length. It's not supposed to have any thickness. But any physical line that we draw, we work with, no matter how sharp our pencil is, no matter how much our capabilities are, if you are drawing a line on a physical mechanism, it will always have some thickness, because if it doesn't have any thickness, we wouldn't be able to perceive it. Try to visualize a one-dimensional line object without any thickness. You cannot, because it simply is invisible. Our minimum perception level goes for two-dimensional objects which has length and width both. So I mean, this might as well look like a line, but if I just zoom in, you're going to see that this line actually has some thickness. It might be small, but it's not essentially zero. And why am I telling you this? The reason I'm telling you this is that because the tip of our pencil using which we are going to draw, they also have some thickness of those. Whenever we try to draw a straight line between 2 points which are pretty close to each other. So for this purpose, I'm going to draw 2 bulk points. Let's say large enough points. Let's say one is here. Let's say one is here. Let's say if these points are pretty close to each other, it is possible to draw. So I might as well show this on the MS Paint, because I can draw straight lines by choosing. So let's say if we have 2 dots over here, let's say one dot is over here, the other dot is over here. So these dots have a bit of a size, which they shouldn't in an ideal case. Points are not supposed to have dimension, but our drawn points do have dimension. And if we're trying to draw straight lines through them, by mistake, it is possible for us to draw quite a good number of lines through them. Let me show you. We might draw a line that looks like this. We might draw another line that might look like this. We might also draw another line that might as well look like this. Let me draw that with light green for a different color. Now, what I want you to see that hypothetically, all of these 3 lines, what did I just do? I messed up. What is this? আচ্ছা, কিছু একটা ঝামেলা করছি আমি আমার কিবোর্ড আর রাইটিং প্যাডের কম্বিনেশন দিয়ে। So disregard this line. I'm going to redraw the green line one more time. Okay. So here, maybe somewhat like that. Okay. So what I'm trying to show you is that provided the 2 points are pretty close to each other, it is possible to draw multiple different lines with different gradients through them. Why is this error possible? This error is possible because our dots have thickness and our lines have thickness. If our dots and thickness, which we were drawing, did not have any thickness to it, maybe it's possible to achieve in a software environment, then this problem would not be occurring. But now we are talking about how can we measure the gradient of a certain straight line on a piece of actual physical graph paper using your pencils and calculators and so on and so forth. So that's the problem we can have whenever 2 points are pretty close to each other. We can have multiple different lines drawn through them who might have different gradients. However, if we have 2 different points, let me draw 2 more red dots. If we have 2 different points which are pretty much of the same thickness maybe, but they are located pretty far away, like since significantly far away, then in that case it's actually quite difficult to draw multiple different lines through them with significantly different gradient. So for example, let's say one of the lines that might join these 2 dots can be aligned like this. The other line which I might draw maybe somewhat look like this. I'm going to draw a bit slanted line over here, and let's see if it matches our requirement. You see, even a little bit of a gradient deviation, it's not perfectly agreeing with both of the points. So maybe I'm going to put this point over here a bit more, and maybe I'm going to shift it right up over here. You see, now we can have a little bit of disagreeing line. So these 2 red lines we have over here, you can see a little bit of gap in between. There is a small white region in between them. So you can pretty much say that these 2 lines do not have the exact same gradient, but you should understand the variation of gradient that you could possibly achieve for points which are really close to each other, and the amount of difference for the variation of the amount of difference for the gradient between these 2 straight lines is actually very, very small. You have a much bigger possibility of error for this location, and you have a much smaller possibility of error for this choice. This is why we prefer to choose to draw triangle between 2 points which are really farther apart from each other, and that gives us a more reliable calculation. এই জিনিসটা কি বোঝা গেছে? আচ্ছা, কার কোনো কোশ্চেন থাকলে বলো। I can say 2 of you give some reaction, which is okay. If you have any question, just let me know. কোথায় ছিলাম? এখানে ছিলাম। So that's the second point, that we should draw a pretty large triangle. And then the third bullet point is that whenever we are trying to draw the triangle, if it is a laboratory experiment, laboratory oriented graph that from which you are trying to get some values, we should always avoid any plotted point, even if they are on the graph. This actually means an example of something like that. Let me just show you over here. Can I get rid of all of these stuffs? Okay, I did. I'm going to bring in the graph one more time here. Beautiful. Actually, I cannot লাভ নাই পেইন্টে দেখাই, এখানে ইজিলি ম্যানিপুলেট করা যায়। ওকে, 200%, 100%। আচ্ছা, তোমরা কি গ্রাফটা দেখতেছো সবাই? মানে গ্রাফটা দেখা যাচ্ছে কিনা? যখন দরকার হবে আমি তখন জুম ইন করবো, কোনো সমস্যা নাই। লেটস সে আমাদের কোন একটা সার্টেন এক্সপেরিমেন্টের তোমরা কি P3 এক্সপেরিমেন্ট করছো কেউ এ পর্যন্ত স্কুলে, লাইক একদিনও কখনো, মানে অ্যাকচুয়াল ল্যাব কখনো করছো কেউ?
স্যার আমাদের ল্যাব করতে পারে
হয় নাই?
না স্যার, আমাদের এইটা ইন্ট্রোডিউস হওয়ার কথা ছিল, বাট কোভিড এসে গিয়েছিল তো হয়নি।
আচ্ছা ঠিক আছে, আমি তোমাদেরকে বেসিক একটা ল্যাবের একটা এক্সপেরিমেন্টের কথা বলি। লেটস সে উই আর ট্রাইং টু মেজার দ্য স্প্রিং কনস্ট্যান্ট অফ এ সার্টেন স্প্রিং। স্প্রিং কনস্ট্যান্ট অফ এ সার্টেন স্প্রিং কিরকম, সেটা হচ্ছে যে লেটস সে উই হ্যাভ, লেট মি ড্র, লেটস সে উই হ্যাভ ভার্টিক্যালি হ্যাঙ্গিং পার্টস। আমি পুরো সেটআপটাই দেখাই। মনে করো এটা হচ্ছে আমাদের টেবিল, টেবিলের উপর এখানে একটা স্ট্যান্ড আছে, ইট ইজ এ প্রিটি হেভি বেস। এই হচ্ছে স্ট্যান্ডের রড, এখানে একটা ক্ল্যাম্প থাকবে। এই ক্ল্যাম্প থেকে আমরা একটা, মনে করো নর্মাল একটা স্প্রিং কে আমরা এখানে ঝুলা রাখছি, ঠিক আছে? এটা হচ্ছে স্প্রিং এর ন্যাচারাল লেন্থ। এখন আমরা এখানে একটা হ্যাং করার জন্য আমরা এখানে একটা হ্যাঙ্গিং একটা মেকানিজম দেবো, যার নিজেরও কিছু ওয়েট থাকবে। সো ওয়ান্স উই সেট দিস ম্যাস, লেটস সে এই ম্যাসটা হচ্ছে মনে করো 100 গ্রাম, তো তাহলে সে একটা সার্টেন ওয়েট প্রডিউস করবে। সো যে কারণে আমাদের স্প্রিংটা এখানে টট কন্ডিশনে থাকবে। তো টিপিক্যালি আমরা এই স্টার্টিং ম্যাসটাকে আমরা ইয়া বলি, কি বলে এটারে, উই কল দিস ডেড ম্যাস। Dead mass মানে হচ্ছে it is the mass that is not going to be part of our calculation, it's only there to make sure that the spring is taut and the setup is stable. তো এখন মনে করো আমরা এখানে একটা মিটার রুল লাগাইলাম, ঠিক আছে? Not to be touching with our equipment, but we can use some set squares to take reading from the meter rule. Let's say we're going to measure the length of this spring up to the very lowest level. So let me zoom in. মনে করো আমরা every single time we want to take some measurement, we are willing to take the measurement to the very lowest level of the coil. তো এটা করার জন্য আমরা যে কাজটা করতে পারি, we can use a set square which we can set alongside the left side of the meter rule maybe. So we're going to align up with this side so that we can avoid the parallax roll right like that. এবং মনে করো আমাদের এই পাশটাতে আছে হচ্ছে সব মিলিমিটার মার্কস গুলা, and we are using a transparent set square obviously, so that way we can very precisely take the reading that where this what this height is currently at. And এটা বেনিফিটটা কি, আমরা তো অ্যাকচুয়ালি এখানে মাপতেছি কি, এখানে আমরা অ্যাকচুয়ালি মিটারের উপর র্যান্ডম একটা সার্টেন একটা রিডিং মাপতেছি। সো এটা মেপে লাভ কি, লাভটা হচ্ছে pretty soon we're going to start to add more loads। মনে করো এরপর হচ্ছে আমরা এখানে আরেকটা 100 গ্রাম লোড দিলাম, তাহলে আমাদের স্পিনটার লেন্থ একটু বাড়বে। সো আমরা starting length রিড করছিলাম, so let's say that's going to be our L0. We are assuming that the spring is not loaded. Then we're going to measure the length for L100, that's for 100 gram. We might attach more, and we're going to record all the individual readings of the meter rule, and then we can subtract the individual values and that can give us a certain reading that altogether how does the spring behave for, let's say, at least 6 set of data. মনে করো how much was the extension for 100 gram, let's say 100 গ্রামের জন্য তুমি একটা, this is the f actually এটা তো আচ্ছা টেবিলটা দেখতে কি রকম হয়, টেবিলটা একটু এক্সাম্পল তোমাদেরকে দেখাই, ডিটেইলসে দেখাই, সমস্যা নাই। মনে করো আমরা যে টেবিলটাতে ডাটা রেকর্ড করব সেই টেবিলটা এরকম হতে পারে, হচ্ছে অবজারভেশন নস নাম্বার। সো এখানে হচ্ছে 1 2 3 4 5 6, we usually prefer at least 6 set of data for your syllabus, and then we can have the individual mass given in gram which is going to produce, and then we can record the L for that mass value, so which can be given in centimeter, and then we can have the value of x. X is basically the extension, which can be also in centimeter, and then we can also have the weight equals to mg, which is going to come in Newton maybe. Okay, so আমরা মনে করো হচ্ছে 100 গ্রাম প্রথমে লোড করছিলাম, দিস ইজ আওয়ার ব্লু ম্যাস দ্যাট আর টকিং অ্যাবাউট। সো লেটস উই গোনা অ্যাড 100 গ্রাম মেবি। তখন আমাদের নতুন আর এখানে আমাদের ইনিশিয়াল লেন্থটা মনে করো লেখা আছে হচ্ছে লেটস সে 12 centimeter, 12.0 centimeter, because with a meter rule you can measure up to 0.1 centimeter, which is 1 millimeter is the smallest fraction of the meter rule. That's how meter rule work. So let's say initial mass is 100 gram, and in that case your length was, let's say, 13.2 centimeter. So your initial value was 12. So if you do the subtraction, you're going to get an extension of 1.2 centimeter. You shouldn't write the centimeter once again in your table, because you have already mentioned the unit in the column heading, so you don't have to write the unit anymore in on the column values. Just write the numbers. And W equals to mg is basically the expression for Newton's second law, that we have to calculate how much mass is over here. For your syllabus, up to all of us, we consider g equals to 10 meter per second squared. So, and here we had how much? 100 gram, that would be 0.1 kg. 100 gram, 0.1 kg, and 0.1 kg multiplied by 10, that is 1 Newton. So I'm going to write over here, let's say 1.0. And then this is our first set of data. And then we're going to have, let's say 200 gram. We're going to attach another one, and we're going to have another ring. Let's say that can be, let's say 14.5. So 14.5 is going to give you a total extension of, to subtract 2.5 centimeter. You might wonder, it's supposed to be 2.4. Yeah, it's supposed to be 2.4, but it might as well be somewhat arbitrary. It might not exactly agree with your mathematical expectation. That's the whole point. তোমরা কি আমার কথা শুনতেছো?
Yes, sir.
হঠাৎ করে আমার নেট চলে গেছিল। I don't know what just happened. There was no fluctuation of electricity. Anyway, something weird happened. I was about to call my ISP, but apparently we don't need that. I can minimize the zoom when recording this. Okay, because I don't want to minimize this. Let's it. I just want to. Okay. Screen দেখা যাচ্ছে? Can you see my screen? আচ্ছা। So এরপর হচ্ছে আমাদের ওয়েটটা আসলো এটা। তো এরপর মনে করো আমরা 200, let's say we're gonna add 100 gram more, so our total mass is gonna be 200 gram. Length is coming this, so we do the subtraction, which is 2.5 centimeter, and then your weight is gonna be 2.0. So you can fill this up for, let's say, six different values, and later we can try to plot these numbers. I'm gonna need a bit more space over here. Okay, later we can plot these numbers with appropriate scale. What is appropriate scale? এটা একটু পরে তোমাদের সাথে পরে আলাপ করব, but let's say we're going to plot our force axis on the y-axis. So these are force / Newton, and on the horizontal axis we're going to plot our extension versus centimeter. So then we're going to plot all these numbers in different places. Let's say those numbers are supposed to give us, theoretically we are supposed to get a perfect straight line, but out of a physical experiment, in almost all cases we don't ever get a perfect straight line. We can have a little bit of haphazard data because of random error and human error, personal error. So our data can be somewhat different. So it is possible that we might come across a straight line that might look like this. Let me draw it red. Straight line. So let's say we're gonna end up with a straight line like this. I'm drawing the straight line first, but I'm gonna show you the position of the points a bit later. Let's say this is the base fit line that we had, which was obtained from multiple different plotted points. Let's say one of the plotted point was here, one plotted point was here, one of them over here, one of them over here, one of them over here. 1 2 3 4 5 1 2 3 4 5. Let's say another one was over here. So we're gonna say this is a pretty well base fit line because we have 3 points on the bottom side, 2 points on the top side, and 1 point is perfectly on our base fit line. So the difference between the points on either side of the base fit line is only 1. So we can consider this to be an acceptable base fit line. Now you can see that for this base fit line, this point is located perfectly on the graph. The third point that I was trying to discuss in our whiteboard that I wrote, that we should not avoid any plotted point, even there on the graph. It means that if we are trying to measure the gradient of this straight line to be able to find out the spin constant, f equals to kx. The equation is actually f equals to kx. That's the Hooke's law, where if you subject the k, which is the spin constant, it can be given by k by f by x, which is basically the delta y by delta x, or gradient of f versus x graph. So that's essentially what we're trying to achieve here. So you should preferably definitely draw a pretty large triangle as best as you can with a good cross point. But if someone chooses to use this exact point, let's say they're going to draw a triangle that looks like this much big, using a point that is one of the plotted points, but because it is existing on the line, they are choosing to use this point. This is something that is not appreciated. We do not appreciate this kind of triangle. The reason is that whenever we obtain certain number of value or certain data from a physical experiment, we consider all of this data to be somewhat errorful. None of these data are considered to be absolutely correct. This is the reason we go for to measure multiple different readings. And then we prefer to draw a graph with all of those values. And from the graph, we prefer to draw a base fit straight line. The entire reason, the key reason for this entire shebang is that we are not appreciating any of these values to be absolutely correct. We consider them to be somewhat errorful. This is why using any of the exactly plotted points, even if they belong to the base fit line, is not considered to be a good practice. It's not considered to be a correct way. So you have to choose a point which is not plotted point. So you might choose any good points over here, any good points over here, and might as well draw a large triangle to go ahead and calculate your gradient. That's how we prefer to calculate the gradient. That's one thing. So এটা হচ্ছিল আমার থার্ড পয়েন্ট, যে আমরা কিভাবে গ্রেডিয়েন্ট ক্যালকুলেশন করি ফর এ স্ট্রেট লাইন। How do we do it for a curve? How do we calculate the gradient for a curve? আচ্ছা, কার্ভের গ্রেডিয়েন্ট ক্যালকুলেশনের মধ্যে কিছু process আছে। একটা জিনিস হচ্ছে, whenever we have a curve, whatever the shape that is, let's say y-axis versus x-axis, let's say we have a curve that looks like this. The key way, the reason we call it a line curve is that a curve has different gradient in different positions. So different জায়গায় তার গ্রেডিয়েন্টের ভ্যালু ডিফারেন্ট হবে। এটা হচ্ছে বেসিক কি ক্রাইটেরিয়া। সো আমি যদি এখানে মেজার করি, এখানে এক ধরনের গ্রেডিয়েন্ট পাবো, একটু পরে মেজার করলে আরেকটা 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 গ্রেডিয়েন্ট পাবো। এখন ডিফারেন্ট জায়গাতে যেহেতু ডিফারেন্ট গ্রেডিয়েন্ট আসবে, সো তার মানে হচ্ছে কোনো একটা গ্রাফে একটা কার্ভের একটা সার্টেন গ্রেডিয়েন্ট মেনশন করে দিলেই সেটা একটা ফুল ইনফরমেশন। আই ক্যানট সে দ্যাট লেটস সে একটা ইকুয়েশন এটা মনে করা হচ্ছে একটা সার্টেন ইকুয়েশন হচ্ছে y ইকুয়ালস টু ফাংশন অফ x। ফাংশন অফ x মানে হচ্ছে x এর রিলেটেড কোন একটা ইকুয়েশন। মনে করে এই ইকুয়েশনটা হচ্ছে x স্কয়ার প্লাস x প্লাস 2, মনে করে এই ধরনের একটা ইকুয়েশন। ধরো বললাম যে এই গ্রাফের গ্রেডিয়েন্ট হচ্ছে 0.2, এটা বলে দিলাম। এটা বলে দিলে হবে না, because এটা একটা curve, because this line, this equation represents a curve. You have to specify exactly at which coordinate is this gradient correct, because different coordinate আমাদের গ্রাফের গ্রেডিয়েন্টের ভ্যালু ডিফারেন্ট। So mentioning a gradient for a curve without the specification of where for which point it is applicable is not an okay practice. It's not a full information. It's a invalid information because it is of no use in most cases. So এই ধরনের একটা কার্ভ যদি আমাদের থাকে, আমাদের ডিফারেন্ট পয়েন্ট ডিফারেন্ট গ্রেডিয়েন্ট আসবে। কথা হচ্ছে ডিফারেন্ট পয়েন্টের গ্রেডিয়েন্ট বের করার বুদ্ধি কি? বুদ্ধিটা হচ্ছে we have to draw a tangent, best fit tangent, and এই best fit tangent জিনিসটা কি এটা আমি তোমাদেরকে ডিটেইলসে দেখাবো। What do you mean by best fit tangent? Tangent কি জি দিয়ে না জে দিয়ে? Tangent জি দিয়ে tangent. So what do you mean by best fit tangent? Best fit tangent বেসিক আইডিয়াটা হচ্ছে যে আমরা যেই পয়েন্টে গ্রেডিয়েন্ট মেজার করতে আছি, মনে করো হচ্ছে আমি এই কার্ভের এক্স্যাক্টলি এই পয়েন্টটাতে গ্রেডিয়েন্ট মেজার করতে আছি, I have to draw a tangent straight line with this curve at this point and draw a pretty big tangent, no big deal, and then follow the same procedure using good cross points of this triangle. You measure how much is the delta y versus delta x for this triangle, and that gradient value would be the exact gradient of the curve at this point. So curve gradient measure করতে হলে কার্ভের ডেফিনিটিভ পয়েন্টে একটা স্ট্রেট লাইন ট্যানজেন্ট রাখতে হবে, সেই ট্যানজেন্টের গ্রেডিয়েন্ট বের করতে হবে এক্স্যাক্টলি স্ট্রেট লাইনের গ্রেডিয়েন্ট যেভাবে বের করতে হয়, এবং ওইটা হচ্ছে কার্ভের ওই এক্সক্লুসিভ পয়েন্টের গ্রেডিয়েন্ট। পুরো কার্ভের গ্রেডিয়েন্ট একটা সিঙ্গেল ভ্যালু হবে না। দ্যাটস দ্য কি প্রপার্টি অফ এ কার্ভ। আর কথা হচ্ছে এই যে বেস্ট ফিট ট্যানজেন্ট, এই যে জিনিসটা আমরা জাজ করবে। হাউ ডু ইউ জাজ যে একটা কার্ভের বেস্ট ফিট ট্যানজেন্ট হয়েছে? এটা জাজমেন্ট একটা প্রসিডিউর দেখাচ্ছি। মনে করো আমি এই পার্টটাকে অনেক জুম ইন করে এমএস পেইন্টে আঁকবো, অনেক জুম করে আঁকতেছি, ঠিক আছে? এখন মনে করো আমাদের এটা দিয়ে জানি কেমনে করে কার্ভ আঁকে, ভুলে গেছি। ওকে, বিউটিফুল। এখন আমি এটা জাস্ট কপি পেস্ট করব, ট্রান্সপারেন্ট দিয়ে দিব, দেন বুম। মনে করো এটা হচ্ছে আমাদের কার্ভের সেই সেকশনটা। নাও ইউ মাইট ওয়ান্ডার এখানে দুটো লাইন দেওয়ার কারণ হচ্ছে আমি অনেক জুম করে জিনিসটা দেখাচ্ছি। এর ভেতরে পুরো জায়গাটুকু হচ্ছে ওই কার্ভের লাইন। সো দিস ইজ এ হাইলি জুমড পয়েন্ট। এখন লেটস সে কলমটা কোথায় রাখবো? হ্যাঁ, লেটস সে আমি এই কার্ভের এক্স্যাক্টলি এই পয়েন্টটাতে ট্যানজেন্ট মেজার করতে যাচ্ছি। আচ্ছা, এটা একটু বড় করে দেই, কারণ হচ্ছে এটা এতটুকু হতে হয়তো আমার এনাফ নাও হইতে পারে। ঠিক আছে, এখন এই কার্ভটা কিরকম হতে পারে? এখন আমি তোমাদের কিছু এক্সাম্পল দেখাবো। এক্সাম্পল দেখানোর আগে আমি আগে একটু একটা রাফ একটা সেট আপ দেখাই যে আমি আসলে কি দেখাতে যাচ্ছি। মনে করো এটা একটা কার্ভ, এই কার্ভের এই পয়েন্টে আমি একটা ট্যানজেন্ট রাখবো। ট্যানজেন্টটা বেস ফিট ট্যানজেন্টটা এরকম হতে পারে, আবার একটু কম হেলানো হতে পারে, আবার অনেক কম হেলানো হতে পারে। এখন কথা হচ্ছে আমরা তো একটা স্পেসিফিক পয়েন্টে ট্যানজেন্ট রাখতেছি, এবং once again the problem that we have that our physical pencils, our physical drawing mechanisms have thicknesses, and that thickness is going to play some important role over here. ওই thickness এর জন্য perfect tangent আঁকাটা difficult, but at the same time we can use that what can I say drawback for our advantage. কিরকম এই জিনিসটা আমাদের বলতেছি, যখনই আমরা একটা বেস ফিট ট্যানজেন্ট আঁকবো, মনে করো let's say I'm going to try to draw a straight line over here. Let me try to draw the tangent with red maybe. Let's say এটা হচ্ছে আমার সেই red line, আমার বেস ফিট ট্যানজেন্টের একটা লাইন। আর একটু কম জুম ইন করতে হবে। আচ্ছা, মনে করো এটা হচ্ছে একটা লাইন। না, এই লাইনটা কারেক্ট হয়েছে নাকি ভুল হয়েছে সেটা আমি বলতেছি না, এটা কারেক্ট হইতে পারে, ভুল হইতে পারে, বাট সেই জাজমেন্টটা আমি কিভাবে করতে হবে সেটা আমি তোমাদের শেখানোর চেষ্টা করতেছি। সো বিয়ার উইথ মি। মনে করো এটা হচ্ছে আমার আরেকটা লাইন। আমি অ্যাজিউম করতেছি যে আমার প্রিন্টেড লাইনের থিকনেস এবং আমার পেন্সিলের নিবের থিকনেস সেম, সো এটা হচ্ছে আমার সেই জুমড ইন লাইন। এখন এই জিনিসটা জাজ করে আমি একটু হ্যাশ করে দেই। মনে করো এটা হচ্ছে আমার গ্রিন লাইন, এটা হচ্ছে আমার গ্রিন লাইন, যেটা হচ্ছে আমার কার্ভ। ঠিক আছে, এই কার্ভের সাথে আমি রেড লাইনটা পেন্সিল দিয়ে এঁকে আমি ট্যানজেন্ট আঁকার চেষ্টা করতেছি। হোয়াট আস্ক এ কোশ্চেন? নো নো নো, মনে করো এটা হচ্ছে আমার ট্যানজেন্ট লাইন। হোয়াট আই ওয়ান্ট টু কনসিডার সেটা হচ্ছে আমার প্রেফারেবল পয়েন্ট, চয়েস অফ পয়েন্ট ছিল কিন্তু এইখানে। আমি কার্ভের এই জায়গাটাতে আমি tangent আঁকতেছিলাম। What you need to judge, let's say you have drawn this tangent and now you want to check whether this tangent is okay or not. You need to see the common part that is overlapped by these two lines. One is the curve, the other one is the straight line. You can see that এখানে আমাদের white region of the paper শুরু হয়েছে হচ্ছে এই পয়েন্ট থেকে। তাহলে এখান থেকে এটুকু পর্যন্ত হচ্ছে ওভারল্যাপ, মানে এটুকু পর্যন্ত আমার গ্রিন এবং রেড লাইনের মধ্যে কমন ওভারল্যাপিং হয়েছে। whereas on this side এই প্লেনটা হচ্ছে এইটুকু। এখন তোমাদের কাজটা হচ্ছে জাজ করা যে এই দুইটা লেংথ অ্যাপ্রক্সিমেটলি ইকুয়াল হয়েছে কিনা, রুলার দিয়ে মেজার করা লাগবে না। would you say these two lines are approximately equal or not? Just by eye measurement, how would you respond to that? বলো, এই দুইটা লেংথ জাস্ট বাই আই মেজারমেন্ট উইদাউট এনি রুলার, আর দি ইকুয়াল অর নট? Okay, it all comes down to your point whether you're going to define these lengths to be equal or not. For example, if you ask me, I am not convinced that they are actually equal. That's my choice, but if you consider them to be equal, then you can move on and go ahead with your working. I'm going to consider these two lengths are not equal because I can see in my eye measurement, I can see that this part is significantly longer where this part is quite smaller. So I would have to reconsider the orientation of this red line so that I can preferably make these two overlap lengths quite equal. So এটা করতে গিয়ে তো আমার ডান পাশে আমার ওভারল্যাপিংটা বাড়াইতে হবে, এই পাশে ওভারল্যাপিং কমাইতে হবে। তার মানে বেসিক্যালি আমার এই রেড লাইনটাকে আরেকটু নিচের দিকে আঁকতে হবে। সো আমার এই রেড লাইনের গ্রেডিয়েন্ট যদি আরেকটু কম হইতো, মনে করো হচ্ছে কি রেড লাইনটা যদি মেবি এরকম হইতো, তাহলে হয়তো আমার এই ওভারল্যাপিংটা আরেকটু কমে আসতো। সো তুমি যত এই রেড লাইনটাকে যতটা নিচে নামাবা, এবং অবশ্যই এই পাশটা উপরে উঠবে, the right side goes down, the left side goes up, then তোমার then you're going to have a smaller overlap on the left side and more overlap on the right side. Your task is to achieve as best as you can with the amount of time that you have available. You don't have to, you shouldn't spend a lot of time for this. And through practice, you should be able to do this pretty easily. That your job is to find out to match these two lengths as best as you can. You don't have to measure by ruler. As I mean, if it is visually equal, then you are good to go. That's what we mean by the term best fit tangent. এখন এটা তো হচ্ছে এই ধরনের সিচুয়েশনের জন্য ইজিলি করা গেল। কিছু কিছু গ্রাফ আছে যে গ্রাফগুলার সিচুয়েশন এরকম সহজ না। মনে করো হচ্ছে একটা সার্টেন গ্রাফ হচ্ছে, আমি একটা এক্সাম্পল দেখাই। মনে করো একটা সাইন কার্ভ, মনে করো একটা সাইন কার্ভ হচ্ছে দেখতে এরকম, ঠিক আছে? এন্ড তোমাকে এক্সামিনার বলছে এক্স্যাক্টলি এই পয়েন্টে গ্রেডিয়েন্ট এই পয়েন্টে ট্যানজেন্ট আঁকার জন্য। আর এক্স্যাক্টলি এই পয়েন্টে ট্যানজেন্ট তুমি কেমনে আঁকবা? এই পাশটা হচ্ছে ওইদিকে কার্ভ, এই পাশটা হচ্ছে নিচের দিকে কার্ভ। দ্য লজিক স্টেজ প্রিটি মাচ দ্য সেম। সেটা হচ্ছে you're gonna have to draw, let me draw with maybe light blue. তোমার কাজ হচ্ছে এক্স্যাক্টলি এই পয়েন্টের ভিতর দিয়ে যাবে, এরকম একটা পয়েন্ট আঁকা, এরকম একটা লাইন আঁকা, যে লাইনটার ওই উপরের পাশে ওভারল্যাপ আর নিচের পাশে ওভারল্যাপ মোরলেস সেম হয়। I mean, I cannot zoom in while this line is still floating over here. So I can see that the overlap is significantly longer on the lower side. It is less on the top side. So I'm going to make it a bit more slanted. And ঝামেলা হচ্ছে আমার ড্রয়িং হচ্ছে খারাপ। Maybe something of like this, where you have approximately equal overlap region. These are not equal, but because my drawing is wrong, I mean, these two sides are supposed to be equal. That's my point that I'm trying to get across. বুঝছো কিনা কি বলছে? যে বেস ফিট ট্যানজেন্ট কিভাবে আঁকতে হয় এই জিনিসটা বুঝা গেছে কিনা?
Yes, sir.
কার কোনো কনফিউশন, কোশ্চেন? নো, আচ্ছা, গুড। আচ্ছা, এটা গেল হচ্ছে এই ডিসকাশন গেল হচ্ছে আমরা কিভাবে একটা সার্টেন গ্রাফ থেকে ফিজিক্যালি ড্রয়িং এর মাধ্যমে বা ফিজিক্যালি আমরা আমাদের পেন্সিল, কলম, পেন্সিল যা আছে, রুলার টুলার আছে, এগুলা দিয়ে আমরা কিভাবে গ্রেডিয়েন্টটা গ্রাফ থেকে ডিরেক্টলি ক্যালকুলেট করে বাই করব। The next part of the discussion essentially the next part of the discussion encompasses যে how do we talk about the change of the gradient. One of the things that I actually moved away from a bit earlier is that a graph gives us basically three set of information. I didn't say three earlier, I'm saying it now. So the first information is that you can always get one coordinate versus another coordinate. You can get how y changes with respect to x. So what is happening to the y value as x value usually increases? We always describe a graph for, I mean, the way we always describe a graph is that what happens to the y variable, what happens to the y-axis variable as the value of x-axis increases. So as the value of x-axis increases, this is always taken to be an inherent information. We don't always say it. So if we say that the y value is increasing, we say this is an increasing graph. It is already embedded within that sentence that y is increasing as x value is increases. So as x value is increases, that part of a phrase is always considered to be hidden, because that's the general way how we describe a graph. As the x value increases, what happens to the y value? Does the y value increase or does the y value decrease? Does it have an increase, which means the gradient is increasing, I mean, rate of increase is increasing, or the rate of increase is decreasing? So that's the second information that we have to judge as well. Okay, Ryan actually asked me a question in the chat that why do you look for a best fit tangent and not any other tangent? The purpose of a best fit tangent is to enable us to measure the gradient of that specific point on the curve. the purpose of the base fit tangent is to measure the gradient of that specific point of the curve. If we are looking for any other tangent, that might be the best fit tangent for any other point, but not for that point. I mean, we can look at multiple different base fit tangents for multiple different choice of points on the graph. That's possible. If you're trying to measure the gradient of a graph on of a single curve in multiple different locations, you can have different tangents, different base fit tangents at different coordinates. But for a specific single point, the base fit tangent essentially gives the same gradient of the curve as the straight line being equal. That's why we are interested for the base fit tangent. I mean, other tangents are not supposed to be base fit tangent. I mean, if I'm okay, I can rephrase you. I can elaborate your question a little bit by this. Consider this scenario. I'm gonna do a pretty big mistake over here just to make my point across. Let's say we have a curve like this. We're supposed to draw a tangent based. I mean, curve too sharp. Let's say we have a curve like this. We want to draw a tangent exactly right over here. এখন এই পয়েন্টে tangent আঁকার জন্য একটা logical choice হচ্ছে we have to have a equal amount of overlap on both sides. এখন এটা যদি না হয়, let's say আমি এই পয়েন্টে tangent আঁকার চেষ্টা করতেছি, বাট সেই কেসে আমার লাইনটা হয়ে গেল হচ্ছে বাঁকা। এখন এই লাইনটা in true case for a curve or a straight line which do not have thickness might well be of this scenario. Let's say এটা হচ্ছে আমাদের curve, আমি এক্স্যাক্টলি এই পয়েন্টে tangent আঁকতে কি অ্যাকচুয়ালি আমি আঁকছি হচ্ছে এরকম একটা লাইন, যেটা হয়তো আমার এক্স্যাক্টলি ওই পয়েন্টের ভিতর দিয়ে যায় না, অথবা আমি হয়তো এরকম একটা লাইন আঁকছি, অথবা হয়তো এরকম উপর দিয়ে একটা লাইন আঁকছি। অ্যাকচুয়ালি দুটো লাইন পারফেক্টলি যেখানে ক্রস করার কথা, ইফ দে হ্যাড জিরো থিকনেস, ও এক্স্যাক্টলি ওইভাবে ক্রস করে নাই। এন্ড ওইটা ফিজিক্যালি অ্যাচিভ করা আমাদের পক্ষে পসিবল না, বিকজ অল দ্য লাইন্স দ্যাট উই প্রিন্ট এন্ড অল দ্য লাইন্স দ্যাট উই ড্র they do have thickness. So that's why we prefer to look for the base fit tangent. Does that answer your question anyhow?
Yes, sir. Thank you.
মানে বুঝছো কিনা?
জি।
All right. The third point, that the third information that we get from any graph is the area information. Area information is actually very simple. Any area calculation is always done by some amount of delta x into multiplied by some amount of delta y. If you have a triangular area, this is basically half into delta y into delta x, because the area of a triangle is given by half into base into height. If you have a rectangle, it is what? Length into height, which is also delta y into delta x. So you're gonna just miss out the half. If it's a parallelogram, base into height, you're gonna miss out the half. If it's a trapezium, let's say if you're trying to measure the area of a trapezium, the area of a trapezium can be written somewhat like this: half into sum of the parallel sides. So let's say it is delta x1 plus delta x2 multiplied by the distance between the perpendicular distance between the two parallel sides. So let's say delta y. So the sum of two delta x will always be some version of delta x. It's going to be the same quantity. So you're going to multiply basically the same thing, that the x-axis quantity multiplied by the I shouldn't write x, multiplied by the y-axis quantity. So basically area of a certain graph, area under a certain graph is always obtained by some form of multiplication of the two axis quantities. So if you have a VT graph representing, let's say, speed time graph, the area of the speed time graph would be v multiplied by t, which is going to be distance. Because if I say this is to be speed time graph, the area is going to be distance. If I say it to be velocity time graph, I'm going to say this is going to be displacement, something like that. So these are the three different information that we get from a graph. I'm going to talk mostly about this gradient observation, that how does this gradient can be manipulated, what kind of different variations can we possibly have, and how to manipulate those variations in terms of information for our use. One of the easiest way, in my opinion, is I'm going to take a small break now, about 5 minutes. I will be back after 5 minutes. If you have to use washroom or anything else, just want to take a 5 minutes break. See you in 5. The next thing that we would like to see is the multiple different variations of gradient. In my opinion, the easiest way to judge the gradient of any straight line is first you have to visualize how the tangent on a curve can work. What I need you to understand is that if you have lines which are, I mean, these are the lines which is said to be more steep, who have a bigger m value, and lines which are pretty close to the x-axis alignment, which are said to be slanted graphs. So this will have a much larger value of del y by del x. So del y by del x will, for this triangle, is going to be pretty large, and delta y by delta x for these lines are going to be pretty small. So first thing is that you have to understand which orientation of lines, straight lines, can have bigger gradient and which orientation of lines can have smaller gradients. Now, if we understand this part, which is very basic, then the next part is that you simply have to judge that if you have curves like this, let's say you have a basic curve that looks like this, and you need to visualize multiple different tangents onto this curve, at least for the beginning part and for the later part. For example, if you try to visualize a tangent for this curve at the beginning side, let's say you're going to have a curve, straight line tangent like that, and you're going to have a tangent like this on the end part. So if you judge the individual possible gradients of these two green straight lines, this is definitely going to give you a much bigger gradient, or this is a much steeper tangent, whereas this is going to be a much more slanted tangent. So the way we describe this graph is that this is y versus x. We say this is a decreasing gradient curve, but you have to understand, as x value increases, y value is still increasing. So if you go for a smaller value of x and if you slowly observe the value for y, you're always going to get a bigger value of y. So as x increases, y also increases, but its gradient, which is delta y by delta x, which can be also written as m, that is slowly decreasing. So we're going to describe multiple different graphs in two different aspects. First of all, what is happening to the y value itself, and what is happening to this ratio. If we ever say that as x value increases, y value decreases, if we have to have that kind of graphs, those graphs might as well look like this. Let me choose red. So let's say we can have graphs that look like this, or maybe look like this, or maybe a straight line that look like this. So these are the graphs that we call decreasing graphs. As x value increases, y value decreases. So based upon this discussion, we can have actually 6 different type of exclusive type of graphs. I'm going to draw them in 2 different set of axis system over here. Let's say this is our y and x axis. This is our y and x axis. We can have increasing graphs of these shapes. Then we can have decreasing graphs of these shapes. If I name them 1, 2, 3, 4, 5, 6. So what I need you to judge is that all of these 3 graphs are increasing graphs, which means as x increases, y also increases. Whereas for these graphs, as x value increases, y value decreases. So one thing is true, for any part of these graphs, if you have a value of del y by del x for any of these graphs, you're going to have for a positive variation of this thing, you're going to have a positive value of this thing as well, because y value will also increase. So if when your x value will increase, y value will also increase, which means your del y by del x is going to be a ratio of positive by positive. So ultimately your gradient quantity will be a positive gradient graph, which basically means that y value is increasing. Whereas for this one, if you consider the variation for del y by del x, for any amount of positive amount of increase of delta x, I mean, if you have observed any of the graph from a smaller value to a higher value, your y value is going to become smaller, which means your delta y is going to be negative, because delta is always measured by final minus initial. In this case, if you judge any of these graphs, let's say using this 6 number graph, if you start to observe from here, let's say at the beginning part, you have a y value of over here. At the later part, let's say your other part is over here. So as your x value increases from here to here, your y value is practically decreases from here to here. So the change of y is actually negative, where the change of x is gonna be positive. So that's the information that you have to observe. So all of these graphs are gonna have negative gradients. All of the graphs all of these graphs will have positive gradients. এই পার্টটা বোঝা গেছে কিনা, পজিটিভ নেগেটিভের পার্টটা, ইনক্রিজ এন্ড ডিক্রিজ? Any question? None, I believe. Okay, if you have question, please respond. The next thing we have to judge is that how does that value of the gradient increase, and for that we have to simply visualize how the possible tangent of these graphs might vary. So number 2 is a line with straight gradient or constant gradient, and over here number 5 is a graph of straight line which is also a constant gradient, whereas number 1 has its m value slowly decreasing. Why? If you observe for the initial part, you will see that the tangent looks pretty steep. For the more on the right side, the tangent is going to become pretty slanted. The opposite will be observed for number 3. For number 3, the initial tangent can be pretty much slanted, whereas for the higher value of x, the tangent is going to be pretty much steep. So number 1 is giving us a gradient that is decreasing. Number 3 is giving us a value which is increasing. So the way we describe graph number 1, which I'm going to write, maybe zoom out a little bit and write over here. Graph number 1 can be said that it is an increasing graph basically means m is positive with decreasing gradient. It means that as x value increases, y value also increases, but the rate at which the y value increases, that is decreasing. Now, if you wonder that what does this actually mean, that the rate of y increase decreases, this actually means that, hear me out on this one carefully, for the same amount of increase of x, we're going to have more increase at the beginning, we're going to have less increase at the end. For example, if you judge this graph, let's say I'm going to use blue maybe. If you take two small sections of equal values of x, let's say one part over here and another equal part right over here, and if we try to find out the relevant delta y for these two equal sections of delta x, and if you try to plot this up on this number 1 graph, for this part you're getting a pretty much this much section of increase, whereas for this much delta x on the later part, for equal amount of increase of delta x, your ultimate delta y increase is going to be really, really thin. It shows that y value will still increase, but it's not going to increase as much, or the amount of increase of delta y, amount of increase of y, which is delta y, that is going to increase, but it's not going to increase as much, which means it is experiencing a small increase. So that's why we say that the rate of increase decreases, or we say this is a graph of decreasing gradient. Number 2 can be said that it is an increasing, number 2 can be said is an increasing graph, same thing, with constant gradient. And number 3 can be increasing graph, which is the same thing with decreasing gradient. Sorry, not decreasing, I bet. Number 3 would be increasing gradient. This is a graph with increasing gradient, which means rate of increase is increasing. এই পার্টটুকু বুঝা গেছে কিনা যে ইনক্রিজিং গ্রেডিয়েন্ট মানে কি, ডিক্রিজিং গ্রেডিয়েন্ট মানে কি, কনস্ট্যান্ট গ্রেডিয়েন্ট মানে কি? আচ্ছা, এখানে যে জিনিসটা হবে, আচ্ছা এখানে আমি একটা জিনিস নিয়ে আলাপ করি, সেটা হচ্ছে all of these graphs by default has negative gradient. Whenever we say negative gradient, we are automatically implying that the value of the gradient is negative. Now you need to understand one more thing. For this consideration of numbers, if you have a number -3, if you have a number of -6, between these two numbers, which one is bigger?
-3.
In consideration of number, -3 is the bigger number because it is less negative. But whenever we are trying to describe the change of gradient, hear me out on this one. Whenever we are trying to describe the change of gradient, we automatically describe whether the gradient is positive or negative, which by default implies its type of gradient. I mean, is it an increasing gradient, or is it a positive gradient, or is it a negative gradient? Beyond this point, we talk about the magnitude of the gradient, which means if I'm trying to describe the gradient behavior for number 4, the description of this thing can be that it is a decreasing graph or negative gradient, negative m. Now that's the basic property. Now, as for the magnitude of gradient, how to describe the change of the gradient's value? Now, to judge that, we might as well consider the tangent orientation. So consider this tangent and consider a tangent over here. Between these two lines, which one would you define as more steep? Which one would you define as more slanted? The left one, is it more slanted, or the right one is more slanted? Which one is more slanted between these two? Can I have a response from everyone else? I mean, like all the people. If you're not feeling like to talk, you can write in the chat window. I'd really appreciate that. Which one do you think is the more slanted one? Yeah. I have 2 reactions. I could go for 4 more. Okay. Now, the correct response is the right one. The right one is more slanted. Now, for those of you who are having a bit of difficulty to understand why should it be the right one, I'm going to make it easier for you. I'm zooming in. Just try to visualize the triangle. If you draw the triangle for this triangle, for this tangent, and if you draw the triangle for this tangent, and then if you are going to try to calculate the value of del y by del x and del y by del x for this one, for which of these 2 triangles this ratio del y by del x is going to be bigger, and for which triangle is it going to be smaller? Which triangle will give you a smaller value, the right triangle or the small left triangle? Obviously, after drawing the triangle, you should be see that this one has a much bigger del x and much smaller del y. So for this one, the m is going to be small, and for this one, m is going to be big. Can you see it clearly now? That why is it having a decreasing gradient? So I hope so. So the way we are going to describe this number 4 graph is that this is a decreasing gradient, which means it has a negative m value, decreasing graph with decreasing gradient. Number 5 is pretty simple, decreasing graph, which is the negative gradient with constant gradient. Number 6, on the other hand, is a decreasing graph, which is negative gradient with increasing gradient. I actually messed up, right? Yeah, I messed up. I was talking about number 6, but wrote for number 4. This was supposed to be increasing. Now, this is supposed to be the decreasing one. I'm sorry. So the reason this is becoming an increasing gradient, because initially the tangent would be pretty slanted, not the perfect tangent. Control Z. This is the slanted tangent, and then at the end you're going to have a pretty steep tangent, more vertical. More vertical means more steep. So that's how we define the tangent behavior. You might wonder that why are these description important for us? I mean, how is this going to be ever helpful for us? Here comes the usefulness. Let me show you. Let's say you are given the VT graph of an object, which looks like this. And it is given in segments. Let's say 0, A, B, C, and D. The question asks you that describe the motion of the object using the points O, A, B, C, D from the graph. How are you going to describe this motion? You might as well have 4 marks in that question. I'm going to write the answer in this way. So hear me out on the description. If you have any question, you ask me. Raise your hand or just ask right away, no problem. I'm going to write it this way. Object starts at t equals to 0 from 0 initial velocity from O to A, it speeds up with decreasing acceleration. Now, why am I telling you this? Because I can see that the V is increasing. 0 is over here, A is over here. So for this segment, the speed is increasing. So the object is definitely speeding up. But what is happening to the acceleration? Initially, you have a pretty large acceleration, which is the gradient. And as you're slowly observing from O to A, you're slowly going to lose the gradient of this curve. It's becoming more and more slant and pretty much horizontal over here, which means right over here, the acceleration is going to be 0 because the horizontal line has 0 gradient. So I'm going to say object starts with 0 velocity, and from O to A, it speeds up with decreasing acceleration. What happens from A to B? Now, what you need to see that between A to B, you basically have two different parts of the graph that we just discussed. Have a look. From over here, all the way up to halfway point over here, if you consider a point over here, for this part, you are having increasing gradient because the graph is becoming more steep. And then from here to here, the graph is once again becoming more slanted. They did not define this point as a specific point in your questions, so you cannot do that either. But you have to somehow incorporate that information in your description for the motion of the graph, of the object. So I'm going to write this answer, my answer in this way. From A to B, the object slows down with increasing deceleration and then decreasing deceleration. I'm using the term deceleration to represent the magnitude of the type of gradient that is for the segment AB, because between the segment for the segment AB, the object is slowing down. So it is basically decelerating, which means for this entire segment, the gradient of the graph is negative. For the first half, the graph is becoming more steeper. For the next half, the graph is becoming more slanted. So I'm going to say it once again like that. From A to B, the object slows down with increasing deceleration for first segment, or you can say first it slows down by increasing deceleration, and then it slows down by decreasing deceleration. So we are having deceleration, which is decreasing. Now, having decreasing deceleration means what? It means at this point, the rate of speed drop was the maximum. You had the biggest minus m over here. This was the zero acceleration. This is also zero acceleration. For this whole part, the speed is decreasing. So this is altogether zero deceleration. You have the maximum value of deceleration at this point. So from here to here, the deceleration increased, and then from here to here, the deceleration decreased. এই পার্টটা কি বুঝা গেছে? হ্যাঁ, তাইসির বলো।
Sure. At that point, does the graph start to get more slanted or something? When it happens, decreasing deceleration.
Exactly. For the segment where the graph becomes more slanted, that's where you are losing gradient, or it means your acceleration is decreasing.
But sir, it's still decreasing, right?
Velocity is decreasing for the whole segment, but
yes, sir. But sir, from point A to B, it's still decelerating, right?
For the entire segment of A to B, it is decelerating. But what is happening to the deceleration? That comes from the gradient judgment. Do you have a high value of deceleration, or do you have a low value of deceleration? Is the value of deceleration increasing, or is the value of deceleration decreasing? The entire segment of AB represents deceleration because it is slowing down. The velocity is decreasing. But how is that value of deceleration? That's it.
Yes, sir.
Did this answer your question?
Yes, sir. It did.
Okay, beautiful. So if we try to move on from B to C, here we have the pretty much similar segment. You can see that C is also one of the crest point of the curvature. So pretty much somewhere halfway over here, we're going to have the maximum acceleration, positive acceleration. And from here, it was zero acceleration. So here to here, the acceleration is increasing. And from here to here, the acceleration is decreasing. So I would write the description like this, that from B to C, the object accelerates with increasing acceleration first and decreasing acceleration later. It's all about how the curve is changing its gradient. Then from C to D, I'm going to write, well, it apparently is that the curve, if I define the C point exactly at the crest, which is not a perfect definition, let's say C was located here, we can see that the graph is losing gradient up for a certain duration. Let's say maybe this much part of the graph is actually a curve. Maybe it apparently looks like it. And for the remaining part, we have a pretty much straight line. So I'm gonna describe the CD segment of the graph, maybe like this, that for the CD segment, the curve slows down with increasing deceleration for the first part and a constant deceleration for a significant longer part after. So for this segment, we have a graph that looks like this. Have a look. That looks like this. So you are having the gradient value slowly becoming bigger. Magnitude I'm talking about. The graph is becoming more steeper for the curvature part. And then for this much part, the graph is pretty much straight line. So it is maintaining a constant gradient. So that's why I'm saying, once again, for the CD segment, the car slows down with an increasing deceleration for the first part, and then a constant deceleration for a significant longer part at the end. বুঝা গেছে?
Yes, sir.
আচ্ছা, what I want you to do, what I want you guys to do, although you don't have to do it, but I would really appreciate, তোমরা কপিতে সবাই কপি নাও, আজকে ডেট দাও এবং হচ্ছে এই 6টা গ্রাফের শেপ আঁকো. Just draw these 6 shapes, y axis, x axis, 1 2 3 4 5 6, and write down these descriptions first. Or I could actually reduce that effort of your kids. I could actually do one thing. I could do print screen and তোমাদের গ্রুপ হচ্ছে এটা, দেখো তো সবাই পাইছো কিনা এটা? Check in your own messenger, not in my screen. Do you have this screenshot? আসছে?
জি স্যার পেয়েছি।
আচ্ছা ঠিক আছে, তাহলে এটার কপি করা লাগবে না, বাট আই উড রিয়েলি ওয়ান্ট অল অফ ইউ টু ড্র দিস গ্রাফ. গ্রাফের এ পয়েন্ট আর সি পয়েন্ট উঁচু নিচু হলে সমস্যা নাই, বাট try to draw roughly this shape. Then I'm gonna say the description of this graph. I'm gonna dictate this whole thing, and I want you to write the dictation and then just compare the dictation with the graph and see if any part looks ambiguous or any part looks difficult to comprehend. So আগে শেপটা আঁকো, তারপর আমি ডেসক্রিপশনটা বলতেছি.
Sir, I have a question.
বলো.
Sir, between the range of B and C, আপনি যে লাইনটা এঁকেছেন এখানে কি প্লাস এফ লিখতে পারি instead of প্লাস বি?
এখানে
স্যার একটু বি আর সি এর মাঝখানে যে লাইনটা,
এখানে
জি স্যার এখানে.
এখানে well you could write, বলতেছি এখানে তুমি জিনিসটা লিখতে পারবা, সেটা হচ্ছে দাঁড়ান আমি দেখাই. What would be a good thing to write over here? I could write plus m maximum, and right over here I could write minus m maximum. See if that makes sense.
Yes, sir, it does.
আচ্ছা সবাই, আচ্ছা আমি ডেসক্রিপশনটা বলতেছি, তুমি আস্তে আস্তে লিখো। ফার্স্টে লিখো হচ্ছে ও এ, এখানে লিখো হচ্ছে the object starts from rest accelerates from O to A point accelerates from O to A point, comma, with decreasing acceleration.
Sir, could you repeat?
The object starts from rest, accelerates from O to A point, comma, with decreasing acceleration, slash. Value of the acceleration decreases. Value of the acceleration decreases. আমি এটা স্পেসিফাই করতেছি একটা কারণে। তোমরা এই যে স্ল্যাশটা দিছো না, স্ল্যাশের আগের দুটো ওয়ার্ড আন্ডারলাইন করো। ডিক্রিজিং অ্যাক্সিলারেশন এই কথাটুকু আন্ডারলাইন করো এবং স্ল্যাশের পরের পুরাটুকু আন্ডারলাইন করো। এটা বোঝানোর জন্য যে এই স্ল্যাশটা কতটুকু ফ্রেজের জন্য অ্যাপ্লিকেবল। লিখছো সবাই?
আচ্ছা, আন্ডারলাইনিং কি করতে হবে এটা একটু আবার বলতে পারবেন?
হ্যাঁ বলতেছি, আন্ডারলাইন করতে হবে হচ্ছে স্ল্যাশের আগের দুটো ওয়ার্ড, ডিক্রিজিং অ্যাক্সিলারেশন এই দুটো ওয়ার্ড আন্ডারলাইন করবা, আর স্ল্যাশের পরে যে ওয়ার্ড পুরাটুকু ফুল স্টপ আগ পর্যন্ত ভ্যালু অফ অ্যাক্সিলারেশন ডিক্রিজেস এই পুরোটুকু আন্ডারলাইন করবা, বোঝানোর জন্য যে এইটুকু অথবা এইটুকু একই জিনিস মিন করতেছে। ঠিক আছে? মাই গড, আচ্ছা আই বিলিভ এটা লেখা শেষ। তারপর লিখো এ ড্যাশ বি। কেউ লিখতে না পারলে বলো, বা স্লো ডাউন করতে হলে বলো, না বুঝলেও বলো, আইল হেল্প। এ ড্যাশ বিতে লিখো the object slows down with increasing deceleration at the beginning and decreasing deceleration afterwards.
So could you repeat?
The object slows down, comma, with increasing deceleration. Increasing deceleration at the beginning and decreasing deceleration afterwards. গ্রাফের সাথে মিলাই দেখো বোঝা যাচ্ছে কিনা।
Could you repeat the OA version, the first one?
বুঝি নাই,
The OA one.
ওই পার্টটা বুঝো নাই?
Could you repeat that?
আচ্ছা, you want me to repeat that?
Yes, sir.
আচ্ছা, ওই তো আমি তো লিখিনি। আচ্ছা আমি বলতেছি, someone else, if I say something different, please alert me. What I said is that the object starts from rest and then accelerates from O to A with decreasing acceleration, slash value of acceleration decreases.
Thank you, sir.
ঠিক আছে, এ বিটা লিখতে পারছো মেজামিন?
Yes, sir.
আচ্ছা, বিসিটা তোমরা একটু নিজেরা লেখা ট্রাই করো। হাউ ডু রাইট বিসি? আচ্ছা আমি একবার বলে দিচ্ছি, একবারই বলবো, তারপর তোমরা বুঝে লিখবা। The object speeds up with increasing acceleration at the beginning and decreasing acceleration afterwards. আম্মুর কাছে যাও, আম্মু পানি দিবে, আম্মুর কাছে নিয়ে যাও, খুলো না। লিখতে পারছো? আচ্ছা, এটা গেল হচ্ছে বি থেকে সিতে, এরপর সি থেকে ডিতে কি হবে? আমি লাস্ট লাস্ট সেগমেন্টের ডেফিনিশন বলতেছি, সি থেকে ডি বলতেছি। আই হোপ বি থেকে সি তোমার নিজেরা লিখতে পারছো। আই এম হোপিং দ্যাট। সি থেকে ডিতে লিখো, the object slows down with an increasing deceleration at the beginning. The object slows down with an increasing deceleration with an increasing deceleration at the beginning, comma, and then a constant deceleration for a significant longer duration afterwards, and a constant deceleration for a significant longer duration afterwards. আচ্ছা, এখন
Could you repeat the last part?
yes, C to D.
Yes, sir. I mean the constant part.
আচ্ছা, আমি পুরোটা আবার বলতেছি। The object slows down with an increasing deceleration for the first part, and then with a constant deceleration for a significant part at the last, or significant duration afterwards, significantly longer duration afterwards. মানে what I'm trying to say is that এই পার্টটুকু ডিউরেশনটা ছোট আর এই পার্টটুকু ডিউরেশনটা সিগনিফিকেন্টলি বড় ছিল। সো ডিক্রিজিং ডিসেলারেশনের পার্টটুকু ছিল হচ্ছে, সরি, ইনক্রিজিং ডিসেলারেশনের পার্টটুকু ছিল হচ্ছে কম, আর এই পার্টে কনস্ট্যান্ট ডিসেলারেশনের পার্টটা ডিউরেশন অনুযায়ী বড় ছিল। এটা সিগনিফাই করতেছি, বুঝছো? তুমি তোমার মতো করে গুছায় লেখো, ওয়ার্ড এক্স্যাক্টলি হুবহু হইতে হবে না, বাট কনসেপ্টটা পারফেক্টলি ট্রান্সফার হইতে হবে। দ্যাটস দ্য ইম্পর্টেন্ট বিট। সবার লেখা হয়েছে?
Yes, sir.
আচ্ছা, এখানে একটা জিনিস আলাপ করি, সেটা হচ্ছে যে এখানে আমি তোমাদেরকে ভিটি গ্রাফ যে জিনিসটা বললাম দেখে আমরা অ্যাক্সিলারেশনে কাজ করতে হচ্ছে। এই জিনিসটা আরো অনেকভাবে হতে পারে। আমি তোমাদেরকে একটা হোমওয়ার্ক দিব, যেটা তোমরা আমাকে ইয়াতে কি বলে ওই যে নেক্সট ক্লাসে আমাকে আমি এটা নিয়ে জিজ্ঞেস করবো, এখন কিছু করা লাগবে না, হোমওয়ার্কটা তোমার রেডি করে রাখবা। সেটা হচ্ছে এক্স্যাক্টলি সেম জিনিস, এক্স্যাক্টলি সেম গ্রাফ, সেম শেপ। সো এই যে এরকম এরকম গ্রাফ, জাস্ট এখানে যদি ডিসপ্লেসমেন্ট দেই, not distance, displacement versus t, the graph is the exact same. In that case, how do you describe the motion of this object? Same graph. Now, how do you approach this homework? The idea is that vt graph gradient হচ্ছে acceleration. Acceleration is given by del v over del t. Displacement time graph gradient হচ্ছে velocity. তার মানে হচ্ছে এখানে যতগুলো জায়গাতে তোমরা object accelerates, object speeds up, slows down বলতেছিলা, এই জায়গাগুলোতে সেখানে তোমাদের আসবে মানে এখানকার এই গ্রাফের গ্রেডিয়েন্টটাই হচ্ছে তোমার ভেলোসিটি। সো যে সকল জায়গাতে তোমার গ্রেডিয়েন্ট বাড়বে ওই জায়গাগুলোতে ভেলোসিটি বাড়তেছে, যে সকল জায়গাগুলোতে গ্রেডিয়েন্ট কমবে ওই জায়গাগুলোতে ভেলোসিটি কমতেছে। তুমি ভেলোসিটি ইনক্রিজকে টেকনিক্যালি অ্যাক্সেলারেশন বলতে পারো, বাট আই এম রেকমেন্ডিং ইউ, আই এম আস্কিং ইউ যে এই পুরো ওয়ার্ডের ডেসক্রিপশনে তোমরা অ্যাক্সেলারেট কথাটা ইউজ করবা না। অ্যাক্সেলারেশন বা পজিটিভ অ্যাক্সেলারেশন, নেগেটিভ অ্যাক্সেলারেশন, অ্যাক্সেলারেশন কথা ইউজ করবা না। You're going to use the term velocity increases, velocity decreases, like that. I want you to be able to apply the term velocity in the applicable cases where you are trying to talk about the change of the gradient. So let's say if it was for the A to B segment for the DT graph, for example, এখানে হচ্ছে A, এখানে হচ্ছে B, I might as well describe this as at A the object was stationary because the gradient was 0. It came to rest. Its velocity increases in the opposite direction for the first segment. I'm not going to say first half because that would imply that this is exactly equal. And the velocity decreased for the later segment, or you can say afterwards. So you have to understand that this whole part for the VT graph, for the DT graph, this whole part would have a negative gradient, right? এটা আসলে কিছু বোঝা যাচ্ছে না, I should erase this. দাঁড়াও একটু মুছে আঁকি। Let's say this was the shape. Okay, so what I need you to understand that for the object over here, I mean, you should see, I mean, try to understand, if you're trying to describe this object's displacement versus time graph for the same shape, what is the initial velocity of the object when it is starting from 0 displacement? What is the initial velocity? Would you say 0? That's it, bolo.
Sir, DT গ্রাফে কি আমরা অ্যাক্সেলারেশনের জায়গায় ভেলোসিটি টার্মটা ইউজ করব সব সময় whenever it's a displacement time graph? Hello.
I would like to correct your question. Let me put out a sentence, see if it makes sense to you. VT গ্রাফের গ্রেডিয়েন্টটা হচ্ছে অ্যাক্সেলারেশন। সো যখন VT গ্রাফের গ্রেডিয়েন্ট নিয়ে আলাপ করতেছি তখন ওই গ্রেডিয়েন্টের জায়গায় আমরা অ্যাক্সেলারেশন টার্মটা ইউজ করতে পারবো, not the other way around. Does that answer your question?
Sir, could you
Repeat.
again?
Sure.
Yes, sir.
VT গ্রাফের গ্রেডিয়েন্টটা হচ্ছে অ্যাক্সেলারেশন. Any single time we are trying to talk about how does the gradient of a velocity time graph changes, we can replace that gradient word with the word acceleration.
Okay, sir.
তুমি এটা জিজ্ঞেস করছিলে না আমাকে?
না স্যার, আমার কোয়েশ্চেনটা ছিল যে হলো যখন ডিসপ্লেসমেন্ট টাইম গ্রাফ থাকবে
Yes,
অ্যাক্সেলারেশনের জায়গায় আমরা কি ভেলোসিটি টার্মটা ইউজ করব সব সময়?
precisely. what you used for the term velocity, acceleration over here, you should be using the term velocity right over here. But there is a catch. Would you say the initial velocity at this point, what would define as the initial velocity of the object, right at the beginning when t equals to 0, at the beginning of the graph? I said that, yeah, bolo.
Sir, 1.
How do you know?
Sir, it's just a hunch.
No, it's not essentially 1, and without having values on the axis, you cannot guess it to be 1. I mean, 1 and 1 what? 1 centimeter per second, 1 kilometer per second, 1 kilometer per hour. If you are trying to give a value for velocity, you need unit as well, unless you are saying it's at rest. Rest is rest. Here's the deal. The gradient of the distance time graph is velocity. I want all of you to judge. Exactly at this initial point, if you try to draw a tangent with this curve, are you going to get a slanted tangent or are you going to get a horizontal tangent? Exactly at this point, what if I just draw the tangent? This is the tangent at the starting point, right? Somewhat like this. What is the value of this tangent? Is it 0 or not? The initial gradient of this curve at t equals to 0, is the value of this gradient 0 or not?
Sir, it's not exact, I think. Exactly 0.
It is definitely not 0 because the graph is actually cutting on the x-axis at some angle. You are not seeing this graph, I mean, to become like this. It's not becoming like that. It's not like that. It's coming and cutting across the x-axis at a specific angle. It's a pretty sharp cutoff, which means the gradient exactly at this point is not 0. It has some value, which means you can say that when the graph, if I was trying to describe this graph, the object starts at 0 displacement with significant positive velocity. And over the duration of O to A, that velocity decreases. Because you are starting with a high gradient, steep gradient, and then you're going to slowly lose gradient on the right. ঠিক না?
Yes, sir.
বুঝছো কি বলছি বলাবান বাকি সবাই? You have to take a good look at how the gradient is working at individual different points, and using that information, I need you to describe that. How would you describe the motion of the object if the same thing was having displacement on the y-axis? This type of conversions and this kind of back and forth descriptions will initially feel to be pretty difficult, might feel pretty difficult for you, but these are the very basic stuff that you need to do well with for a much better grip on the graph manipulation. এই জিনিসগুলো যত easily করতে পারবা, that's my part. I'm going to make it easy for you over practice, over time. তোমাদের ফিউচারে সব ধরনের গ্রাফ নিয়ে কাজ করা তত সহজ হবে। And একটা জিনিস absolutely true. I mean, there is no escaping graphs. If you are in the study of science subjects, you will have to deal with graphs. No matter how long you want to study, all the way up to PhD, post-PhD, multiple PhDs, doesn't matter. You are dealing with something relevant to sciences, something relevant to numbers, for example, you have to handle graphs. So you have to learn how to handle graphs properly. It's important that you learn how to handle graphs. বুঝা গেছে কি বলছি? এই হোমওয়ার্কটা থাকলো, আমরা নেক্সট ক্লাসে ইনশাআল্লাহ এরিয়া নিয়ে আলাপ করব, এই হোমওয়ার্কটা ডেসক্রিপশন নিয়ে আলাপ করব, and we're going to see some practical examples from other question papers as well. আজকে এটুক থাক। Thank you very much. আসসালামু আলাইকুম।
So,
So, sir.
Awesome.